Hello everyone, in this video we will implement driver identification system using a deep learning architecture known as fully convolution network LSTM. As you know that most of the cars these days are equipped with advanced sensors and you can easily acquire the sensors data using any Bluetooth device. Once you acquire the data, usually containing speed, RPM, throttle position, steering angles and many other features particularly associated with the driving behavior of a driver, also known as driving footprint. Now, a car using an AI solution can learn the driving behavior of its owner. Now, it's nearly impossible for a thief to learn all the skills related to the driving behavior of the owner of a car. Based on this knowledge, we can design car anti-theft system. As it's a time series classification problem, we will implement it using Python as a programming language, and we will use TensorFlow for training and deploying the deep learning architecture. My name is Shanul. I am a PhD student at Inha University, South Korea. My major is computer vision and deep learning. Let's get started. This is the outline of my today's video, and you can skip this part if you already know the core concepts, and you can directly dive into the implementation part. I will explain the motivation first, why we need to identify a driver, what are the possible ways to do it, what is time series classification. For the dataset part, I will skip the acquisition because it's very difficult to cover everything in single video. Rather, I will be using the available dataset, which is OCS Lab dataset. We will implement everything line by line for driver identification system. What's the motivation behind all this? Why we need driver identification system? As you know that based on any OBD sensor, like you can search on Google OBD2 adapter onboard diagnostic system, it's a protocol name to acquire the CAN bus data, controller area network bus data. As a deep learning student, I don't need to dive or learn everything related to the car architecture. Rather, one thing I must know that it's a time series problem, right? So you can install or buy any OBD2 adapter and then you can get the data using Bluetooth. You can get it on your laptop or you can use the mobile phone as well. So one of the solution is anti-theft system, right? So which is the topic of today's video. Other solutions are possible, such as, for example, for Uber and Cream, we can also analyze the driving behavior of a driver, such as if a driver is taking sharp turns, or if, for example, a driver is driving aggressively. We can make an application based on deep learning architecture, for example, for Uber or Careem, such as if a driver is driving very harshly, so we will give him less stars. And if a driver is driving very safely and the fuel efficiency is very high for a particular driver, then we can give him more stars. And then prior to selecting any driver, the customers can use this feedback and can select their drivers correspondingly. Another applications could be for insurance company, like we can use the driving behavior of a driver and then insurance companies can monitor their drivers correspondingly. Now the question is, what is time series classification? As a deep learning student, as we know that we have several domains of the deep learning where we can apply the deep learning. For example, one of them is computer vision, in which the input is image, right? We have image, and most of the time the outputs are not image, such as sometimes the output is boundary boxes, sometimes it's the classification score or classification like dog, cat, and so on. So in case of the computer vision problem, always the input is image, but the output is these kind of things. Similarly, in case of the image processing, the input and output are both images, like we have input as image and output is also image. And we can use the deep learning to perform filtering to remove the noise and sometimes to increase the quality of image for the enhancement purposes. Similarly, in case of the natural language processing, we have input text sequence. So deep learning utilizes the grammatical rules, and based on the feature extractions of the grammatical rules, it can predict the next sentence, sometimes the word, perform the autocorrections, and many other applications. The reason to explain all these different domains is to differentiate the time series classification problem from them. In case of the time series, we have the input as sensor data. One particular example is mobile sensors, in which gyros and accelerometers are used. You might have noticed in your daily life that when you move from one place to another place, particularly from your home to office or office to home, walking has been detected. You get some notification that walk or run has been detected, right? So deep learning architecture based on the sensors data classify the time series such as walking, running, going up, going down, and many other classes as well. This is called as HAR, human activity recognition, which is time series classification problem. So what is time series? For example, in this case, this is a car sensors data, and every second we are getting some data. For example, 2 seconds, 3 seconds. If we have 1 hertz data rate, then definitely we have this time series. And if you want to classify like this part as an A driver, and for example this is to another driver, and so on, so this is called as time series classification problem. Similarly, another example is stock exchange as well, in which we have sensor data or the data particularly related to the stock exchange, and then we can predict new time series as well. Now that we have known that our problem is time series classification, let's discuss the dataset. As I told you that I am skipping the acquisition part for this particular video, we will be using dataset which is famous OCS Lab Security dataset, which has been used in many world famous competitions, right? Let's discuss the features of this dataset. There were 10 different drivers, for example A to J, different drivers. The frequency of the data acquisition was 1 Hz. There were 3 different trajectories. One of them is shown here. For example, this is trajectory 1. Second trajectory is this one. And third trajectory is this one. I'm just giving you an example. Every driver has driven 4 times each trajectory, right? In order to learn everything, right? Deep learning needs a lot of data. If similar single trajectory has been driven by same driver 4 times, it will be easier for deep learning to grasp all the skills or features associated with the driving skills of that driver. So this again, this makes this dataset a very nice candidate to select. So that's why I selected this dataset, and it is based on CAN bus. And these are some examples, like it contains long-term fuel trim, engine coolant, and so on. So there were total 51 different features. Like CAN bus data, you can get 51 different features. These are few examples, and they have selected the best 15. I'm not discussing how they have selected the 15 best over here. So they have selected the 15 best, and they have performed some statistical features with that. They have performed some machine learning to identify the driver, which is our today's topic. These days, most of the advanced deep learning architectures are used rather than statistical techniques. I will tell you shortly. This is the deep learning architecture I'm going to use for this particular video. The name says fully convolution network, LSTM. So actually this part is fully convolution network, and this part is LSTM part. As you know that the convolution operation reduces the filter size. If I have, for example, 50 into 50 input, and if I use the kernel size or filter size 3 by 3, so the formula is input minus k plus 2 into 0 padding divided by stride and plus 1. So if I don't have any 0 padding and stride is 1, then 50 minus 3 is 47 plus 1 would be 48 will be my new feature size, and it will be keep reducing. If I increase this kernel size, so definitely it will be keep reducing in normal convolution operations. However, in case of the fully convolution network, they call it fully convolution, they use one of the features, they use full size, like using 0 padding. The size remain the same, in this case 1D CNN, and it performs some 0 padding so that all the time for at every layer the size of the convolution matrix or feature size remains the same. That is why it is called as fully convolution network. And other features I'm not going into much detail. So FCN, fully convolution network, was very famous for time series classification, until when in 2017 paper like this is the FCN-LSTM network has been introduced, in which students from US University, they proposed this, and it was a major breakthrough. The reason, let's discuss why it was a major breakthrough. This is the time series data, in which in this way like vertically, the time changes. Like this is 1 second, this is 2 seconds, and so on. Horizontally, we have different variables, right? So that is called as multivariate data, right? So this horizontally we have multivariate data, and this way we have temporal data, also known as time sequence. They grab both temporal data, like temporal data they use convolution operations. So for example, if I get first 60 rows, okay, so 60 rows into, I have 15 features. Previously I've used 15 features, right? So 60 into 15 will be my input size. So in this case, 60 into, for example, 15 will be my input size. 60 into 15. Using the dimensional shuffle, we will get 15 into 60, right? So LSTM is getting the multivariate. Over here, it is getting the multivariate data. However, in this case, it is getting the temporal. Like temporal means the time, related to time. The convolution operations is related to the time, while for the LSTM, it is related to multivariate data. So both kind of features, like multivariate features and the temporal features, has been concatenated and get the output data as a class, like B, C. For example, this was A and this was B and any other driver. So the time series classification, it was a major breakthrough, and after that many other researchers have also used this. One particular example is IEEE Transaction, which is one of the top journals. They have used in 2019 the same architecture for driver identification. Previously it was for human activity recognition, it was proposed, but they have used for driving identification. This is the beauty of the architecture, that as long as the nature of the problem is same, such as time series classification problem, it's the same, so you can also deploy that. Over the time, in 2019, they have also published their another paper by defining more insight to this network. So that's make them very successful as well. And I don't want to dive into much details of LSTM and convolution network or what's happening inside, because when we publish any video on YouTube, we do not know what kind of audience we have. Let's dive into the implementation part. For implementation part, I will prefer to use the Anaconda, as we can make some environments in it, and it contains multiple libraries and IDEs, and like IDEs like Jupyter Notebook, Spider, VS Code, and one another IDE is PyCharm. So if you are familiar with any of them and you want to use, you go ahead, you are free to use, right? For this particular video tutorial, I will be using Jupyter Notebook because it is based on the web browser. So it's based on web browsers, and you can track your outputs and you can make very nice notes as well. So that's why I will use Jupyter Notebook. Otherwise, you are free to use any of them. Let's start the implementation part. And the good thing about the Jupyter Notebook is that you can make very nice notes using this hash key, and after writing this hash, you can convert your cell type to the markdown and it will be converted to very nice notes. So you can make your or create your notes while programming. And another good thing about the Jupyter Notebook is that you can easily trace back all of your answers, right? So we will see shortly. Let's execute this code. Shift enter is the command, and the reason why I have executed this code is that it is reading the 94,000 rows of this CSV file. So I thought that let's execute it. So while it is taking some time, let's discuss what's going on over here. So the first thing we are importing is pandas library, and you can easily install it using pip install pandas. Similarly, for matplotlib, you can easily install using pip install matplotlib in your Anaconda command prompt. And for NumPy, you can easily import it, like you can install like pip install NumPy correspondingly. So the first line is that pd.read CSV file, and we are using the pandas library to read the CSV file. And let's see what is inside the dataset, from where I get it. This is the GitHub link. I will paste the link in the description of the video. And this is actually basically the code implementation of IEEE transaction paper. You can search this title in the Google Scholar, so you will see the paper as well. But over here they have done automotive grade Linux based implementation on Raspberry Pi. So I'm not going into detail of that, while I will be focusing on only driver identification part. So if you go to the training folder, this is the folder. If you go to the training folder, you will find the CSV file over here. So already there, and the code you will find inside the train anomaly. For this tutorial, I am just I will shortlist some code part and I will re-implement everything again. So that is the reason I am executing this code. Another thing I would like to inform you over here is that they have also provided you the actual dataset link, right? So if you click this link, you will be here, and this is the driving dataset which have been used in many other competitions as well, and you can read it about that using their website. You can easily download if you want to download the source of this file, so you can easily download. Description is available, and the driving time is 23 hours, and the driving length is about 46 kilometers. And the driving path was from the Korean University and to some place, right, to some stadium. There were 10 different drivers. They have named it A to J, and so our classes will be 10. Okay, so once you download, you don't need to download from here, because as I told you, they have already provided you in the GitHub link. If you go to the training part, you can easily download this full data test CSV. That is what I am reading right now, and it's already done. It's 3, it should be 1. The reason I was practicing before, so that's why. So please ignore it. We will discuss everything line by line. So this is the file I have read so far using pandas library. Let's see what's inside. If you download the code, you will have all of this. So I have already opened this CSV file, the full test, the data test, which I have already downloaded from the corresponding path. So if you see, there are 51 different columns, right? So we call it features, or as a deep learning student, we will call it as a features. And you see fuel consumption, accelerator, pedal value, throttle position, and so on, and so many different 51 features are here. And at the end, they have provided you the time in seconds. As you see, 1, 2, 3. So that is why it's 1 hertz. So every second we are taking 1 sample, right? And at the last column, the classes are defined. Like this is class A, so this is labeled data, right? So this is class A, H, and up to J. There are different, and you see over here, you can see that they are random. Okay, so this is the actually raw file which we have got from the Bluetooth sensor of the CAN bus, right, using OBD2 sensor or OBD2 adapter, right? So you don't need to care about how it comes over here. So as a deep learning student, all you need is to just check that this is the format of the data. Okay, so once we know what is inside it, so we have shortlisted only 15. This is the good thing about the pandas. Once we read everything, and let me show you something else. So there are total 94,000. If I go to the end, almost 94,000 rows are here, right? And rather than 51 different features, I have shortlisted only 15 of them, the most important one. And how I come to know about this, that the dataset providers, if you visit their paper, they have already mentioned, like if you visit this paper, they have already provided you that which one you have to select. This is the paper, right? So if you just download this paper and download the paper, and you will get to know that what are the important features out of 51, and it's up to you. You can also use all of them as well. So we have gone through all of these lines, what's going on. We have shortlisted these 15 columns, and another thing is over here we are doing anomaly detection as well. This is optional part. I just included it because it was already available in the code. Let's discuss it as well, but it's optional, it's not important over here. If you read the documentation svm.oneclass svm over here, you will see different things. So what is one class svm? It is for anomaly detection. And what is anomaly? For example, over here we have the data x. Let me zoom it for you. Okay, so this is the data, is at 0.44 and 0.45, 0.46. So you see over here that 0 and 1 does not belong to the series of that. So this makes sense, like 44 and 45 and 46. This makes some sense. These three guys are related to each other. But however, this 0 and 1 is not. So it can be anomaly, right? Anomaly means that something different than the trend, right? So this is the anomaly. So you see over here, after doing it, it will return you that this is -1 and this is also -1. Why? Because these are the anomalies. So whosoever are not anomalies, the one class SVM will send you back the 1, right? For rest of them, it will give you -1, right? So in order to detect the anomaly, you can easily use scikit-learn built-in function, which is one class SVM. You can also design yours, but sklearn has already provided you. So it is for anomaly detection. So the reason why we have done we are using in our own model is that you can easily detect the anomaly, and if for example we have sensors, right? The car sensors may have, for example, it can be attacked by someone or any thief or anyone, it can be attacked. So in order to detect that all the data is definitely genuine or legitimate, so definitely we have to verify it. Okay, so that is why we are using one class SVM to detect the anomaly, right? There are plenty of other algorithms as well. You can use other as well, and these are the parameters, and you can also see what are the, like over here you can see the parameters. This is the kernel, and different kernels you can try as well. The default is RBF, the root based basis function, and it's polynomial one, and similarly gamma, they have already explained what's going on over here. So you can change it as it's optional, so that's why I'm not going into much detail. So NU is the upper bound and gamma and kernel coefficient, so you don't need to worry about this because this is for anomaly detection, which is kind of out of scope for this video, but anyways we are doing it just to, you can easily get the anomaly as well. So if you fit on this data, like before going into the deep learning, before providing this data to the deep learning, we already know that, for example, this will have provided us -1 and 1, right? So whosoever is -1, it means that this is anomaly. Whosoever is 1, it means that the data is legitimate and the data is okay to go, right? So once we have already done this part, let's go for further pre-processing part. Please give me 1 second so that I can just copy some stuff from my notes. Okay, so this is my second part, pre-processing of the data. Let me move this to, let me make another, and let's, to save time, I'm just copying my code from my notes and I will execute it. This has not been executed yet. This has been executed. So pre-processing of the data. So now we have 10 classes, as you know, from here you have 10 classes, right? A to J, right? The last column is about the data, about the label, right? This is the classes, right? These are the classes. A to J we have classes, we have 10 classes. What's going on over here? Let's execute and then I will explain everything to you. So what we are doing it, for example, over here we are separating each, like a C in classes, like in the label we are taking A, we are searching A in all the data, and then B and so on till J. Why we are separating each driver's data? The reason is that for a good and nice distribution, because for example, if I just, in the deep learning, as you know that we have to divide training part and validation part. If I divide it randomly, the problem is that, for example, 3 drivers will come, the result in the training maybe 3 drivers comes up, and in the testing maybe some another driver comes up. So we have to make sure that in our training part and validation part, each driver data should be there, as well as we have to make sure that it should be random as well, otherwise deep learning will be overfitted. So in this case we are just doing it, what we are doing it that we are separating each driver over here, and this is the training data and validation data. We are separating everything based on the time as well. As you can see over here, again let me show you, the timer is for every driver separately, right? So this is we are using as the timer, the clock for every driver is different, so we are utilizing that in order to initialize our indices, right? So for the last part, when it become equal, so for every driver the last trip we are taking it as a validation set. So the number of the trips are 4, and for training we are using 3, and 1 is for validation. Similarly, for number of the trips over here are 6, and we are taking 5 as a training one and 1 for the validation, and so on. So for everyone, the last one we are using it as a validation, as a validation one. Listen, so NV is for validation and NT is for training. So we are just separating till this point. What we are doing is that you see over here we are just driver plus the C is the number, all the classes 1, 2, 3 and so on. The reason C changes because in previously when we were using C, in this case when we were using C it was ABCD, and later when you use range so it become 1, 2, 3. So that's why over here it's 0 to 9, right? So that's why the C number has been changed. So what we are doing over here is that we are separating, we are doing it into the frames. So we are converting it into the frames. So for this part, let me show you one another thing. I have also published a paper on the same topic, driver behavior identification, 1 year ago, and I'm not sharing my code for this particular video. And over here you see, over here we can do it for every driver. We have WX like a window, and we have a jump as well. So in the time series classification you have to find the appropriate window size and the jump, right? So you can do it. So I have also compared my result. This is my proposal network, and I have compared my results with this. Okay, and I have created a lightweight driver behavior identification system as well. So I'm not going into detail, but for this particular video we are only focusing on FCN-LSTM based driver identification system. So over here what's going on is that what we are doing is we are making the 60, the window size is 60. Let me show you that again, the window size. So this is the window size, right? So we are taking the window size from every data, and then we have jump. So WX is the window size and DX is the jump. So the window size is 60 in this case, and over here what we are doing it, we are 60 rows, you can say that over here 60 rows, or it is equal to seconds as well. 60 means 60 seconds data, right? Because okay, so 60 means that this data and so on. So like 60 rows I am just taking, for example, right? And every second we are getting one sample, so that's why every second. So I'm taking then every 60 seconds I'm separating everything, and I'm having one, I'm leaving one of them, I'm dropping one of them, you can say, and then next 60 and one next 60 and so on. So ultimately I will have 15 into 60, right? So you see 60 into 15. Why 15? Because our columns are 15. These columns are 15. Otherwise the total number of the features over here were 51. Okay, so there are 51 features, but we are only taking 15 out of them. These are the 15 selected ones. So that is why it is 60 into 15. So the reason why it is the one, so 16 to 15 is each frame size, and let me use the calculator over here just to tell you. So we had 94,000 rows, right? And if I divide it into 60, so it is about 1566, and I am dropping one per each driver, so that is why it's 1551. Okay, so approximately, so that is why we have these much frames. So I have selected 60, then I leave something, and then I selected 60, and then I leave something, and then up to so on, right? So these are my data now. So right now I have the data, and now I have to let's check the okay. So if I take 0th one, so it will give me 16 to 15. If for example if I want to see the data, so definitely it will have this data, right? So it has the data. Okay, let me do it again to save the time. Or okay, let me copy from my notes, so that's why. Okay, so now what we are doing we are doing some further pre-processing. As I told you before in the start, that for pre-processing we are only doing the normalization. Previously in previous papers there were some statistical techniques. For example, if you just read this paper, they have used this old paper, so they have used many pre-processing like median, standard deviation, mean, and a lot of other statistical techniques as well for pre-processing part. The good thing about FCN-LSTM, what we are going to do is it do not require any kind of further pre-processing. Only it requires is the normalization. So over here we are performing only normalization part, right? Okay, so let's execute it. And one another thing, extra thing I'm doing over here, that I am dividing first 17 to 30.3 is the 30%. So from my data I am dividing 70% as a training and 30% as a test. And from my training again I am dividing randomly, I'm just picking the prediction part, right? So it should be from test part, but anyways if we can convert into test part as well, so it's up to you, right? Because it should be from test part. So let's convert it into test part. Okay, so let's convert it into test part. Why? Because it should not be training. The reason is that whatever we are training, we should not get it back, right? Okay, so what we have done over here, that we have first 70 to 30, and out of 30% we are again converting our test data set into prediction data set, right? The prediction is the one which we will use real time, right? Just to show you the real time. And the random state I'm just 31. Okay, so this is done now, and let's check everyone's shape. So the training is 1085 into 60 into 15 out of 1. What was my size? Let me check this data size, shape size. It is 1551 into, okay, it was also already there. So out of 1551 I took 1085, and let me check my text part. This is my test, sorry, and 419. And what about my prediction? So the reason is it's only 47, so it's okay. So out of 1085 I took these two guys. So if you plus all of them, I hope you will get this answer. Okay, so okay, and let me show you something. So the first like this is 0, and this is 1, and this is 2. So I have, okay, so 16 to 15 is my size, right? Let's implement FCN-LSTM, right? And let's make it like this, and let me copy again from my notes, and this is the network. Okay, let me run the network and then we can discuss. Okay, so what's going on over here? The FCN-LSTM, the famous paper for the, okay, let me show you the original GitHub link. So as I told you before, that these paper driver identification have used FCN-LSTM, which is actually not their own code. They have used the FCN-LSTM previously used for the time series classification. Sorry. Okay, so this is the original paper from US University. They have already implemented everything. You can also go and check, but their implementation was on time series general classification. And This is the original paper, right? So what's going on, I will refer this. We are getting import, then dimension shuffle, and so on. Okay, so let's discuss over here. So we have input shape over here. In our case, it is 1 and 2, which is 16 to 15. So we are getting 16 to 15, and permute is for, this is our dimension shuffle, right? Dimension shuffle it is. Okay, so this is our dimension shuffle. And over here, so you see over here, another thing, important thing is that LSTM is very less. The LSTM cells are very less used over here. So that is the beauty of this time series FCN-LSTM, is that there are two benefits. Once we do not need to only need to normalize, and we do not need to perform a lot of input pre-processing. Second benefit is that it is very lightweight. The reason is that because of this LSTM, because of this architecture, we can only use only 10 unit cells, and it is easy to get it right. And the dropout is too much. Anyways, we are taking from the original authors, and after dropout we are doing it. So this is our one. You can say this is our, let me check again. So this is our one dimension shuffle and LSTM and dropout. So we are reached over here, right? This point we are reached, okay, till this point. And okay, let me have space. So this was my first, this was input, this is my first link, and then what we are doing here, let me put a space. So this is our second part, which is this one. So count 1D, then bench normalization, ReLU, and all of them, and then we are performing global pooling, and then we have to concatenate them. So what we are doing over here, so okay, global pooling was with that, and let me concatenate. So this is the part, and we are concatenating both of them, as we have only 10 classes over here, so that's why we have this is 10. Otherwise it could be like if we have 20 classes or any other classes, we can have it, right? And one another thing is that they were using softmax classifier, and the original paper they were using softmax, but for this particular implementation what we are going to use is they were using sigmoid. So anyways, we will go for this implementation, which is for driver identification. So the general this paper was not for the driver profiling, it was for generalized time series classification, and this particular paper is for driver behavior profiling. So once we have the model, okay, so let me check the model summary again, just to have a quick overview. And you see we have input, this is shape, and you see very less parameters we are using, right? So because only okay, so 1D CNN we are using, and it's only 8, kernel size is 8, it's 1 by 8, right? Why? Because it's 1D CNN, right? Because for time series classification we can use 1D CNN, and we can also use the 2D CNN as well. It will make it more lightweight, because I have also proposed in my paper that for the implementation part you can also use the depthwise spawn 2D, and you can also make it more lightweight. So okay, so well, over here we will go for the similar implementation. Okay, so this is the model summary, and these are very less parameters, and it's a lightweight. And once we know what is going on, let's train our model. Okay, let me change. So this, let's train our model, and I hope it will not take much time. So the third advantage was, okay, let's discuss the advantages of this network again. The first one, we don't have to do a lot of input pre-processing. Second important was it is it's lightweight, and third is it reads in few epochs to very high accuracy, and we will witness soon. Let's start the okay, so you see I started from 16, and within few you see epochs it's going very well. You see 53 and 50, 60 and so on, right? So okay, within 20 it has achieved 73, and let me run it again, or for example let me run it for 10 again. Okay, so that it reaches little more 73, and it was very less epochs, but anyway, so ultimately it will be 30, right? Actually I'm using the same, so okay, now it is starting from 73. Why? Because I have used because it is stored, so that's because of the Jupyter notebook, right? So it is okay, so it has reached to 82, and the validation accuracy is 82, otherwise the accuracy is 95. So I think it's more than enough, but if you want more epochs, 30 epochs is nothing, right? Most of the people use hundreds and so on. Let me run it again. It will become 40, for example. Let me retrain again, so it's again starting from 75. Okay, and I hope it will go further, but if it does not, then we will leave it. Okay, again it has started 81. 81 is also a good accuracy, not bad, but anyways, I think what I have done over here is that the reason it could also achieve up to 96% accuracy as well. Let me show you, because previously when I use, but one thing I changed over here is as you see, when I was doing over here, I changed my splitting, right? So X train and X text, and again I split it. So text, the validation is very less, so that is why it is achieving less accuracy. If you change this, it will be go for 96%. So let me show you as I told you, let me show you my notes. So previously I used this kind of, okay, so I did not use from X train, I did not use that like X text over here, so I achieved up to, within few epochs I achieve up to, you see, 99% accuracy as well. But anyways, as we are doing it lively, we are implementing right now, so it's okay. Even if it is 80%, it's okay. So let's so I have told you the reason why it is happening over here. So anyways, let's go for, with the 81 is okay, we are fine, and let's save the model. Okay, so now that we have saved the model, I can evaluate now my model as well. Okay, this is the evaluation, and let's check our history. The good thing about the TensorFlow is that if you store the variable in the history, you can really you can plot it as well. So this is my model accuracy. You see, so they are not, they have still have a lot of margin, because my train accuracy is very high and the test accuracy is less, the validation accuracy is less. So yeah, you can say that over here we have a kind of little bit overfitting as well, but I will not go to improve it over here. We can improve it, as I told you before. How we can improve, I have also shown you that up to 96% we can also achieve the accuracy as well. Okay, so anyways, I will go for the next part. So after training everything, let's have some another test. So what's here? The reason over here is that, as I told you before, in the first step what we did is we perform anomaly detection, and we have fitted our everything into we use a support vector machine. Okay, so but even with the putting the anomalies, we want to see what will be the accuracy, right? So we have achieved 81% accuracy, as you can see over here. We have achieved the validation accuracy was 81%, but over here we can, like, the rates, like different rates up to 50%, we have adding some anomalies, right? And we can do a random 1 or 10 rows as well, and up to 7 sensors we have done. Okay, so to column and rows, so these are my columns, these are my rows, and checking what will be the impact. And the anomaly, I'm saying that, for example, I'm multiplying 311 over here, and I'm adding 30,000 just randomly, 3,000 over here, and even though I have added the anomalies, but still, even without any anomaly detection over here, you see, I have not done the SVM. I can also done So as I have already fitted, I will find, as I told you, I will find all the location where the -1 is here. Okay, after that, and I can average them as well. Okay, so once I find, for example, over here there was an anomaly, so I can use this one and this one to average it, right? So I'm not correcting it over here for anomaly detection, but I'm just want to check that after putting anomalies, what is the impact. So you see, when there is 0%, okay, there was 81, there was 0% rate of anomaly, we got 81% accuracy on single row, and the 10 rows definitely it's the same, it must be same. Why? Because for both cases we have not put any kind of anomaly, but in case we have put the anomalies, you see, when there is less anomalies, their accuracy is a little bit change. But as long as we are increasing the anomaly, you see the accuracy goes down, definitely, because there is anomaly and it is impacting the accuracy of the network. So this code is already been provided to you. In case of you go to train and train anomalies, you open it and you will find in the bits and pieces all the code over here. So I will share the link so you can find it. So it's a very good study that if you want to check what will be the impact of anomaly or noise, you can say, of the noise on your deep learning architecture, you can check it. Okay, once we have trained, we have put and we have seen what would be the impact of the noise or anomaly on our network. Once we have finalized everything, let's see okay, the deployment part. So in the case of the deployment, definitely after training everything, I have already saved my model over here. You see, I have already saved my model. Once I have saved my model, I'm here just running. So this is my deployment part. So you can use Raspberry Pi, any hardware device, okay, for the deployment. Let me change to the, okay, once you see that impact, and now in the deployment part, let's read the model. Why? Because we don't need to train everything in the deployment part. We don't need to train everything, and once we can read the model. So let's say that now the drivers are actually driving the car. So what I need to do, I have already trained model, I will read the model. Okay, and as you see over here, let me show you something. As you see, our training, our data of the model is trained on this kind of like 1 into 60 into 15. So I must have one dimension as well, right? So 1 into 60 into 15 is my dimension, right? The training shape. Okay, so my training shape must be like, you see, I put x train, and the dimension of the x train is 3-dimensional, right? So that is why I need to take care of it. So I will add one dimension, okay, into 0. 0 means the first, right? So 0, 1, 2, right? So 0 is the first one. So I will put, okay, when I see, okay, so this is the x predict. Would when I, if you remember, when we were splitting the data, where was the data? Okay, over here we were splitting the prediction, we have split it, and for prediction part we have not seen this prediction. The deep learning part have not seen any kind of prediction. For validation it has the test training as well, even the validation part it has not seen, but anyways the prediction we have not used anywhere, right? So prediction data we have already split it. And if I check the shape of this, let me first check the shape of this. So this is the shape, so which is not needed actually. The shape is I need is after, oh, this must be shape. Okay, this must be shape. So I need to put the shape. So 1 into 16 into 15. Okay, 0 means the in the near. If I put -1, for example, it will do it at the end. So anyways, I need to put it on a 0. Once I put it like this, now I can predict my live data. So in the, if you see in the training part and test part, I use both of the, like my labels as well. I use my label and my data as well. In this case I don't need the label. Why? Because I will only provide the data, only one data, right? because the label I'm expecting, although I have it, but I will use for the prediction part. So let me check what is my prediction. If I execute, there are so many things. So what I need to do is that these are the probabilities actually. So I have to check what was the probability of that. So I need the 0 was the maximum part, and let me check. So you see, our model has predicted successful. Why? Let me check show you. So we have 10 drivers, right? 0 to 9. So you see, these are our values. Let me check first the shape. So as you saw, 47 data we have not shown it to our hardware, and we are just checking it. So if I go with this, you see my prediction was 0. Okay, my prediction was, so this is my prediction. I got it from my live data from this, right? So I just gave it to him, my live data, and it has predicted. I have not shown my, in case of my prediction, I have not shown him my label. Okay, so this is my prediction value, and this is y predict is my stored value, right? So now it means that our model is 100%, or our model is performing very well, right? Although its accuracy is 81% so far, but you can increase it to 96% as we have discussed already. Let's check other. For example, I have let me predict. Let me show you this. So okay, let's check for example this one. Okay, or any 0 or 0 1 2 3 4. Let me check the fourth one. Okay, so what I will do, I will change it to 4. Okay, okay, this is don't need to do it, but anyway, this is the one. I hope it will give me the prediction 4. Sorry, 4 0 1 2 3 4. The answer will be 6, right? It's my fourth index. So I put the fourth index, and I'm expecting 6 as answer. So it was the 6 as answer. So my prediction is 6, but let me check what is my stored value like inside it. So definitely we have already seen that it's 6, but anyway, let's show. So this is 6. So my prediction, the model prediction is 6, and actual value was also 6. So y predict is my actual value. Okay, and this is the prediction is by my model, right? So okay, let me, so this is as well. So I'm whatever I have predicted, like the model predicted, it was actually up to the mark. So let's say any random, because it's 47, so let's do it 10, right? So let me execute this. I don't need to execute these others, and I have a live data. Okay, 10th is my index, right? Remember, 10th is my index. How we can check? These guys should be same. These two guys should be same, right? This must be 10. So my answer must be 5. You see, my answer is 5. So the model predicted the exact value, which was actual values. This is prediction. So I can, these line of code, deployment part code, you can just deploy in your Raspberry Pi or any other hardware, and you can connect, and whenever you will get the data, all you need is to just apply the live data prediction, and you will get the answer. Over here we have seen 0 to 9, we have driver names. You can convert it into the naming convention as well, as we are using the sparse categorical. Let me show you for the, you see, sparse categorical cross entropy we are using. That is why we convert it into 0 1 2 3, but anyways you can also use it ABCD as well. So it's up to you. So our model is predicting very well, and this is all from the driver identification system. You can make your driver prediction, and for example, if the way it can be deployed is that, for example, if any thief is, you can say that if any thief is driving, for example, if you are not the one, you are the 5, and 5 is not driving the car, any other guy is driving the car, based on his all data sensor, based on this sensor data, if anyone else is driving data, then definitely you can make a system that the car should be stopped after 1 or meter or few meters, it should be stopped, right? So it's for a 60-second data, so at least you need 1 minute, right, in order to grab one data. So for 60 second, not minute, sorry, in 1 minute or 60 seconds, if this driver behavior identification will identify within 60 seconds that this guy is, who is this, right? So if he's thief, then car will stop. And usually that is the reason in my case I use 40. I have reduced this in my paper. This is my paper. I have reduced this time. Why? Because this is very critical. We should not wait for 60 seconds. If you start waiting for 60 seconds in order to this, you see 40 seconds I have proposed up to 40 seconds. So if our driver is waiting, or driver profiling algorithm is waiting for 60 seconds to get a good or confident prediction, then it's not good, right? So we have to reduce this time. So I have reduced to 40 seconds, and you guys can try and make more robust model, and you can reduce it further as well. So in my model, within 40 seconds you will get to know either you are driving the car, owner is driving the car, or any other thief is driving the car. You can make it stop as well, and we have practically deployed it in connected car environment. But anyways, you can, if you're interested, you can see our paper as well. We have actually deployed everything in the connected car environment using the edge computing. Okay, so that's all from today's video. Thank you so much for watching and listening everything, and that's all from my side. Keep watching and supporting our channel. Thank you so much.